All right, we're going to get started. So it's my privilege to start this session on cognitive computing. And like a lot of the data scientists and computer scientists in the room, we always like to start with definitions. So I'm going to disappoint you because I can't find a good one. In fact, what Wikipedia says is that at the present, there is no widely agreed upon definition for cognitive computing in either academia or industry. And this is a problem and an opportunity. I think as a community, we can come together and start to think about how we define what cognitive computing is, and more importantly, since we're talking about the future, what we want it to be. So instead of focusing on words, let's start with an image. What do you see here? You see a baby bringing in data from reality, from its experiences. And something's happening in that head. What we want cognitive computing systems to do is ingest data from reality, sample the universe of experiences, and do something with that data, and translate that data into something useful, like biomedical knowledge. Eventually, we become really, really good at that. The idea of taking data and turning it into knowledge is something uniquely human. Eventually, machines will outpace the ability for humans to turn data into knowledge. Eventually, machines are going to amplify that ability. But how do we get there? We really have to understand how humans do it before we can even approximate how machines do it. That's not to say we want to copy exactly what machines do. We don't want to do, exactly what humans do. We don't want to replicate the human brain in a machine. What we want to do is understand the basic principles by which the human mind translates data into knowledge. Understanding those principles is going to help us design computer systems that could biomimic that very special effect. And again, we don't want to simply create machines that do what humans do, because we have humans that do what humans do. And we have a lot of humans, and we can crowdsource. We need machines to go far beyond what humans do. We don't want a machine that can operate like a physician. We want a machine that can help the physician solve problems that no physician can solve today. So if you think about turning data into knowledge, it all happens in our head, but there's a dichotomy in how it happens. There's certainly data that we can sample from reality, and we can abstract that data into higher order concepts and patterns. But there's also something that happens in the reflection of our mind. It's not something that happens in reality. It's that understanding and storage of knowledge is not something that happens outside, it happens inside. And understanding that, I'll argue, understanding the difference between the two, the difference between processing knowledge and processing data and understanding knowledge is fundamental to solving these problems. Okay, so cognition itself we can define, that's easy. Cognition is simply the mental action or process of acquiring knowledge and understanding through thought, experience, and senses. You heard about the Internet of Things, you're going to hear a lot more. You're going to hear about systems, you're going to hear about language, how we deal with language. These are all data that we can turn into knowledge. But again, we have to go beyond that. We have to start thinking about the future of where a machine starts to think for itself. So as much as we could supervise the learning of machines, we have to create machines that can create their own knowledge. We call that autonomous learning. Now, autonomous learning happens in the brain, so we can dissect the brain and look at the human neocortex, look at the properties of the human neocortex, and there have been some great books to describe what those properties are. There's many. I'm going to just choose two of my favorite. One is On Intelligence by Jeff Hawkins, came out around 2004. When I first read this book in 2004, I was awakened. I was awakened to the fact that we can go beyond expert systems. This idea of having statistical models and and machines that simply crank data in a different way, and then we put duct tape around them and we create makeshift solutions, to something that could be universal. A universal way of representing knowledge, a knowledge representation framework that can solve these problems. And Ray Kurzweil has also written a very nice book, very same idea, taking neurons, taking hierarchical structures in the neocortex, and translating that into knowledge. So we started to experiment with this about 10 years ago. I had just terrific fun creating things like hypergraphs, and you're going to hear from Walt about what the next generation of industry scale graphs look like. But the really impressive thing is that we could take a principle of the brain, hierarchical representation of memory, and replicate it in computers using very simple data models. So the idea of nested hypergraphs, being able to create a recursive abstraction, that's turning data into knowledge. Machines can do this. We just have to figure out how to implement it. Important to implementing it is understanding also a philosophy of knowledge. We call that epistemology. If you don't have a good epistemology, you're not going to get very far. You're going to create these dumb expert systems that all they do is go recover existing knowledge. They'll never create new knowledge. The future requires us to have a really good definition of knowledge so we could build universal systems. And the best definition I've found for what knowledge is a justified true belief. Now, that all starts with a belief. In our human imagination, we can create a belief. I believe that what I'm looking at is a cell. So if I look under a microscope and I see these shapes and patterns and colors, I'm going to have a dialogue, an internal dialogue with my mind that's going to start with a Bayesian belief propagation. I'm going to jump to the conclusion that I'm looking at a cell, then I'm going to resample the data space until I recognize that, yeah, my belief is justified by the data that I'm looking at. That cycle, the dichotomous cycle between the imagination and reality, that is how I can come to the conclusion and know that I'm looking at a cell. So that's where knowledge lives, in that intersection between a belief and reality, a model and data. The really cool thing is these models, they can come from your imagination, or they can come from an autonomous self-learning machine. I can come up with 12 beliefs a day. A machine could do 1 billion hypotheses a second and sample a lot bigger data space than I can. So we're not talking about small incremental improvements in intelligence. This is not new. The idea that a belief, knowledge is a justified true belief, was proposed by Plato. We just have to adopt that same epistemology in how we create these next generation of machines. The other real epiphany for me was, well, what do we mean by imagination? So for that, let me give you a little story about Rain Man. So a lot of you have seen this movie. Rain Man is this incredible individual who knows a lot of things, could regurgitate a lot of things, could process a lot of things, but he doesn't have a lot of imagination. It turns out that Rain Man is a real human being, a real person. His name is Kim Peeks. And Kim Peeks would have this incredible ability to read phone books, just go to the library and just ingest things. But he had no imagination. He did not have the ability to create new knowledge. All he could do is help regurgitate what he's already learned, but in a way that none of us can do it. If he's read a phone book 10 years ago, he'll remember Becky Sue's phone number. We can't do that, but our databases can do that. So learning about Kim Peeks could help us understand where imagination like that comes from. Well, what's lacking in Kim Peeks' brain is the corpus callosum. That's that structure at the top in a normal brain. It's lacking at the bottom. What that structure does, it lets the left and the right brain communicate. It lets your imagination and your perception of the world become one. That dialogue between yourself, that's what's lacking. That ability to do that is, we have to start thinking about our machines being able to do that, because ultimately that is what allows us to do that. Now, where is that network of network? In the brain, it's that white matter. Tim will tell you that's the Internet of Things. If we can create an intelligent Internet of Things, we're going to have databases talking to each other, because databases are things. And if they're intelligent agents, like Watson, we can go from Rain Man, regurgitating facts, to many Watsons, many types of cognitive computing systems linked together, and that gives us that path from Rain Man to Einstein. So the future is really bright. We're going to have this ability to connect the left and right brainness and bring in imagination, and ultimately, it's that dialogue between the two minds that's going to allow machines to improve themselves. Because we don't know how to build the ultimate machines, the machines will build themselves even better. So I'll leave you with two things. Humans empower machines to translate data into knowledge, step one. And then step two is machines amplify intelligence. So with that, let me pass it over to the next presenter, and we'll talk a little bit about how we take a very special type of data, language, and translate it into knowledge.
Good morning, everyone. I'm going to spend 10 minutes or so talking about clinical natural language processing. Before I begin, I'm going to put the technologies I'm going to present into perspective. Why do we care and what we can accomplish with them? I'm going to present the data that is used in developing these technologies and a couple of resources that you can make use of and play with at home, in-house, and develop your own technologies at your institutions. So when we're talking about healthcare, we have three main types of data sources that we can work with. We have the numeric data that comes from recording of vital signs from patients. We have clinical notes that are in the form of narratives, and those are stored in electronic medical records. And then we have images, right? Results of X-rays, MRI, any kind of imaging tests. The interesting type of data is the narrative data, the clinical notes, because this data is not the same depending on the country, depending on the language you're looking at. So if you want to explore it and develop mathematical solutions, it becomes more challenging because those solutions don't transfer across the space. Now, assuming that you have some sort of a mathematical solutions, you can actually answer very interesting research questions. You can look at cohort selection. You can do phenotyping by just exploring the information that is stored in electronic medical records. You can identify groups of patients that have very similar properties. You can develop decision support systems, and those have tremendous value in simplifying the day in and out of a health practitioner. We're talking about integrating common practices, treatment outcomes, and success rates into the toolkit that a health practitioner gets to work with. And you can also develop quality assurance systems, and insurance companies are developing a lot of technology in this space because you want to be able to answer questions like who saw these patients and were the treatments in adherence to the protocols that we have prescribed and we like to follow. Now, when we develop clinical natural language processing tools, we're basically building a pipeline. What goes into this pipeline is a blob of medical narrative, right? A blob of medical notes. What comes out of the pipeline is information that's useful for answering the research questions that we're interested in. And in this case, if we are to look at a short medical narrative, we can build some magic in the middle of our pipeline, and we can extract information like concepts that are not showing properly over here. But basically, we can identify diseases, medications, and other types of information that can help us answer questions like, what is the historical health of this patient? What kind of medication is the patient under? And the advantage we're having by using mathematical solutions, automated solutions, is that you don't have to read through dozens of medical records, historical records for the given patient. What's interesting is that on top of, the slide is not displaying properly, but on top of concepts that are extracted from the medical narrative, you can also extract relations. And those are critical because knowing for which disease the medication was prescribed, or knowing which medications interacted between each other and it resulted in a side effect for this given patient, is very useful in deciding what's the next step in the healthcare of the given patient. When building those natural language processing solutions, we're basically teaching machines how to think. And similarly to how you take a child and you show the child an object and you tell it, oh, this is a slider changer, you take the machine and you tell it, this data is an example of a disease, and you should always annotate this as a disease. And we have developed as a community a set of data sets that contain these annotations. Two of the most commonly used and comprehensive data sets are the I2B2VA research data set. This is a collection of de-identified medical records that contain annotations for concepts and relations. And also the Share eClef eHealth data set that contains annotations on top of medical records coming from the MIMIC2 database. There are a couple of other interesting and useful data sets, and I just want to point out to the ClefER data set that's annotated across multiple languages. And that's very useful because you get to evaluate how your solution performs across, let's say, English and Spanish and French. And you can have this healthcare system that works in the United States as well as in Spain and in France. Once you have the available annotations, once you have the resources available to teach your system how to think, there's various approaches we can take in developing solutions. And back in the day, the most common approach was what we call a rule-based approach that is basically implemented on top of this idea of if A and B, then C. We call this system expert systems, right? Because they encode the knowledge of a health practitioner that has a lot of expertise, domain expertise. The problem is that the rule-based systems break often and then don't generalize properly to new data. And because of that, the community has started to adopt statistical approaches where we basically take this burden of having to design rules and we leave mathematics to explore the data and infer proper knowledge and infer proper formulae out of it. Hybrid solutions are also a common approach to designing clinical natural language processing systems. They're more powerful because they either combine hybrid, rule-based with statistical solutions, or they are what we call ensemble methods, where similar to the design of a deep learning model, we basically stack multiple systems and we combine their predictive power. And last but not least, in the clinical NLP space, we started to see more and more of deep learning solutions being employed. And those are very powerful because, as you've heard recently, it's not that we need a tremendous amount of data in order for these deep learning methods to work properly. We are able to do transfer learning and adopt information from other domains in the clinical space. If you are interested in doing work in this clinical NLP space, there's a couple of resources that I would encourage you to use because they provide tremendous value. I'm talking about clinical ontologies that have been developed by the Natural Library of Medicine, UMLS, and SNOMED. And also, if you just want to play with an off-the-shelf implementation of a clinical NLP, there are a couple of resources, unfortunately only available for English. CTAKES, RxNorm, and MetaMap, those are implementation of NLP algorithms that you can just plug and play with. I'm going to skip the slide in the interest of time, and because we also have another session that's going to focus on deep learning later on. But I want to conclude by saying that we've seen tremendous progress in clinical NLP, both in English and in other languages. And with the advent of deep learning, we're now able to build more robust and more scalable solutions across languages. And what's also encouraging is the fact that these systems are getting transitioned from the lab to the clinical practice, and they're actually improving the quality and the effect of healthcare. Thank you.
Okay. I think you're up, right?
Great, thanks. Good morning. My name is Walt Gall. Thank you, Spiro. Thank you, Anthony, for the invitation and the organizers. So I head up healthcare for a small business unit inside of Intel. We're a recent acquisition last year, and we sit inside of Intel's new technology group. So think of this as a division that's working on some of the cutting-edge platform technologies inside of Intel. And one of the key themes that I want to kind of address today is not only Intel's history in optimizing workloads in the context of healthcare and life sciences, but also leveraging AI technologies to optimize workflows, specifically in the clinical and life sciences practice. The other takeaway is this idea of hybrid computing, which Andrea just referenced, but I'm going to have a little bit of different perspective on that as it relates to the opportunity here. So Intel, as I mentioned, has a long history in really accelerating precision medicine as it relates to research and applied care, optimizing those workloads. And with the Saffron acquisition, as well as other machine learning and deep learning assets over the last couple of years, from machine learning to deep learning, such as Nirvana and Movidius, and Saffron being part of this end-to-end stack, we're now in a position to start looking at how Intel can actually accelerate precision medicine beyond just optimizing workloads, but getting into software decision support. So a little bit of a history. Spiro, this is where you came from as far as TGen and the partnership with Intel and Dell, where we basically participated and contributed to that acceleration of compute to basically go from biopsy to initiation of treatment in 12 days. Which exceeded the goal of that study, which led to being able to stop progression of cancer in 60% of patients. So this was a milestone in this particular domain, and that was just the beginning. So starting with that last year, and then moving beyond just accelerating primary and secondary analysis, but really getting into where we are today with regards to starting to look at the other data sources as it relates to other variant alleles. As it relates to taking an artificial intelligence approach coupled to this accelerated compute. And so, essentially, Intel has a long history in, bringing various standards-based programmability, being able to implement on-prem and cloud, and having the best state-of-the-art supercompute. And now, in the context of the scalable system framework, is now focusing on artificial intelligence. So with that, I'd like to talk about this opportunity to actually go after hybrid computing. So we know in the deep learning and machine learning field, there has been some talk about the need for a memory. And Saffron has been doing this for 16 years at actually scaling out the ability to do a memory-based representation and a memory-based reasoning. So building a cognitive reasoning system or an autonomous learning system where you actually can do one-shot learning. In other words, you have a quasi-perfect memory of that incident that happened. Even if it only happened once, under those contextual circumstances, you actually have a memory of that. And so I would sort of look at the classical as well as advanced machine and deep learning, and the promise that has as it relates to creating the appropriate data pre-processing and perceptual computing. The metaphor that we draw is you can't watch a movie without eyes and ears as far as understanding what you're watching, but the actual recollection or the imagination of what's going to happen next, you actually need a memory. And so the combination of these two approaches, being able to look at the high dimensional associations that Spiro alluded to by taking a graph or a hypermatrix approach to this, where you're able to actually reason across that sparse, individualized entity association data based on the context and the information distance between those entities and events. That's what's possible, and that's what Saffron's been doing. So as an overview of Saffron as a cognitive reasoning system, we take a model-free, rule-free approach to automatically learning the connection patterns between the entities. And as a biomedically trained scientist who came to Saffron with a systems biology background, I was very attracted to this idea of creating a persistent knowledge store at that individual entity level, whether it's a patient, a provider, a device, a drug molecule, and being able to capture, just as the human brain does with our associative memories in our hippocampus, looking at the counts as well as the context in space and time, and then being able to couple that to the calculation of a context-dependent information distance. Some of you who follow the field are familiar with Komorogov complexity, or a universal cognitive distance that can look across the higher order structure that's represented by this approach and be able to reason across that and look at the relevant attributes close to an event that you're trying to monitor or predict or prescribe. So the ability to, assimilate this information, whether you're doing similarity analysis or the mathematical reciprocal, looking at anomaly detection, or even novelty, something that you've never seen before, understanding the network of interactions that makes that novel, and then ultimately being able to adapt as new data comes in, being able to learn autonomously in real time, but also being able to query in real time at scale. From 5 data sources to over 100 data sources, we've been doing this for many years. So being able to have this representation based on memory, as well as this memory-based reasoning, coupling those two is really the secret sauce of what Saffron does quite well. So a couple of use case examples that we've been doing. If you look at various omics fields, what's common between all of them is there's an association network. So moving beyond association studies and more semantic graph extractions, if you could actually look at a semantic and a statistical data representation by looking at this, taking this hypermatrix approach, the accuracies that you can actually generate are quite impressive. And so this was a survival curve analysis where we're actually looking at microRNA gene expression from liver tumor biopsies, where we were 90% correct to the exact week over a 70-week period. And you can see the errors here appear quite chaotic across the range, which suggests that the errors may be due to coverage. And so the idea is to go beyond the 90% accuracy just with one data source and start coupling this to other data sources. Another example is in the imaging domain, where we are actually working with Mount Sinai and Joel Dudley. We published earlier this year looking at restrictive cardiomyopathy versus constrictive pericarditis. This is a hardball use case in the imaging domain in interventional cardiology, where protocol accuracy is around 64%. And so we compared ourselves to other machine learning approaches, such as support vector machines, neural networks, random forest, and we showed that we not only had an accelerated learning curve in this study, looking at this high-dimensional analysis with echo metadata, but using an associative memory ensemble classification approach, we were at 94% accuracy with 50 subjects per group plus a control group. And we published this in 2013 with just 15 subjects per group, and then 50 subjects per group just this year, showing the opportunity here with accelerated learning. And our goal is to then move into looking at, obviously, other conditions related to cardiovascular disease, looking at left ventricular diastolic dysfunction and how that might progress. We're also interested in the interplay between cardiovascular and oncology, for example, where we're interested in looking at various data sources, gene expression, whole genome sequencing, and clinical data, and looking at chemotherapy-induced cardiomyopathy. We're also doing a study with one of the children's hospitals on the East Coast, looking at epigenetic data, plus those other data sources, including the imaging pathology data sources. So this gets me to workflows, optimizing workflows. We've had a lot of success in the intelligence community at tackling the single hardest cognitive workload. That is actually identifying the appropriate workflow as a recommendation system. And if you actually look at the possible sequences in the tens of thousands of analysts around the world, with the number of sequence and steps that are involved, it's more than the number of stars in the universe. And so can an associative memory cognitive computing approach be effective with so little training data? And the answer is yes. With 20,000 sequences to learn from, we're at over 97% accuracy. So we see this as an opportunity in healthcare where clinical workflows are prevalent. We know a lot about them as far as retrospective data sources, and we actually want to look at physiological and quality and cost outcomes as it relates to the expanded data sources going beyond the EMR. So looking at the various data marts and an opportunity to optimize workflows. And that's what we're currently focused on as a future direction, and going beyond those data sources, but also looking at claims across the journey of the consumer. And lastly, I just want to talk about a future direction as it relates to collaborative data share frameworks. This is something that Intel's been working on over the last year, where there's a federated data cloud of omics, imaging, clinical data. The three founding institutions, Oregon Health Sciences, Ontario Institute for Cancer Research, and Dana-Farber, where we're looking to minimize the data transfer, secure the data sharing as far as that collaborative data share framework, and accelerate precision medicine as far as enabling the interaction with these various shared data sources amongst these institutions. So in summary, Intel offers an end-to-end scalable system framework, accelerating workloads, optimizing workflows with AI, and here are some links that you can go to learn more about Saffron, as well as what Intel's doing in the distributed computing and analytics space. Thank you very much.
Thank you, Walt. Very exciting. All right, Tim, you're up.
They're all probably wondering, I've just talked, so I'm talking again. I'm pinch hitting for somebody who couldn't make it. I already introduced kind of the general topic. What I probably want to spend time with you in the next 10 minutes, if I get my mouse clicking. Okay. Well, I'll just start talking. I don't really need slides. Okay. Here. So maybe what I'll spend 10 minutes talking to you guys about is how I've been thinking about this problem of the Internet of Things, and at least where I think there's huge investment opportunities and big gains to be made. So I started out this talk, I said, well, things aren't people, and let me just go a little further with that. So I'll give you 5 reasons why they aren't. So number one, there are going to be way more things connected to the internet than there are people. If you listen to the John Chambers speech, he will talk about 500 billion things connected to the internet. Well, that's literally 100 times the number of people there are in the world. I was talking to a guy at Ascension Health a couple of months ago. He goes, oh yeah, that's already happened at my place, right? So we're going to have way more things connected than people. 2, things can be where people aren't, right? So things can be in your stomach, smart pills. Things can be out in the middle of the Gobi Desert, right? Things can be a mile underground in a coal mine, so things can be where people aren't. 3rd, things have more to say. I just gave you the example of wind turbines, 400 sensors. Actually, modern combine harvesters have 300 sensors sitting on them. So they have way more to say than people ever could. Things can talk much more frequently. I gave you the example of a coal mining machine that has vibration sensors that run at 10,000 samples per second. And the last one, and we can debate this, is that things can be programmed, right? People can't. So for all these reasons, I believe we're at this discontinuity, meaning why would technology that was built for the Internet of People work for the Internet of Things? And so let me just take this framework, which I developed just to help people who don't speak technology understand a little better about how to think about the new world of Internet of Thing applications. So I'm going to start with the thing itself, okay? One of the things that people probably don't realize is what has driven a lot of this is sensor technology, right? Sensor technology has gotten enormously cheap because of this thing, right? You probably don't realize it, but you're carrying around, there's 12 sensors on this, right? Magnetometers, barometers, et cetera. Accelerometers at this point in time are basically quantity 1 cost about $2, right? So the advent of much lower cost sensor technology is pushing this whole thing. And coupled with, as we already know, very low cost computing, very powerful low cost computing. So the question that I've been speculating on, because if you look at most machines, and in healthcare, go look at the gene sequencers, the MRI scanners, right? The compute environment's fairly unsophisticated by our point of view, right? And so you begin to wonder, well, if you look at this, it's got ability to connect to 12 sensors. It's got a pretty powerful computer in it. It actually already talks to 3 different kinds of networks. when are we going to see a cell phone inside every machine? I mentioned I teach in China. Part of it's because I like to go and eat food, but the other part's I get to meet people. So this last time I was there, I met up with one of my former students who's at Xiaomi. So I don't know if you don't know Xiaomi. They are the world's largest manufacturer of cell phones. They build 80 million of these a year. Amusingly enough, they're starting to saturate the Chinese market, so they're starting to look at India, but they're also starting to look at next generation products. So I said, well, like what? And so they wheel out, and you'll love this because this is a very localized product, an air purifier, right? So if you're at all familiar with the big Chinese cities, air quality is a real problem, right? So it's an air purifier. Amusingly enough, if you open up that air purifier, guess what you see inside? A cell phone. If you know the history of Xiaomi, the guy that went over to run engineering over there was one of the original Android people. So you might guess there's an Android operating system sitting in there. My personal opinion is there's going to be a whole new stack for things. It's not obvious that it's going to be Windows or Android, et cetera, and so I think there's huge opportunity there. Second, let's talk about connecting the things. So things are going to be connected in way different ways because things are not where people are. So we feel fairly content with, oh, I've got 4G and Wi-Fi, I'm cool, right? So you may have heard of this company. It's called Sensium Vitals. They actually built a vital sign monitoring patch that they put on you when you go in the emergency room. Well, those guys had a design constraint. They said, I don't want to put a bunch of battery packs on it, so I have to go wash the battery pack and recharge and all that. So they wanted to use disposable batteries. Well, as soon as they used disposable batteries, there's not enough power to drive Wi-Fi. So they ended up building if you're technical, a Zigbee-like mesh network. So there's a lot of work in networking. If you're at all familiar with Sigfox, LoRa at the low bandwidth, very long distance, low power networks, all the way to, I'm actually working with a young company that's doing 60 gig mesh networks, so very high performance, very short range. Security, we're not going to do security the way we did it for the Internet of People, glomming on at the end of the day. Even if you think about it, why are we going to be able to make our things change their passwords every 6 weeks and put an exclamation point in it? We've got to come up with another way, and I believe there's a bunch of opportunity there, particularly to leverage what's happened in blockchain, et cetera. So if you move out of connection into collecting the data, I'll tell you a little story. There's one of the large oil and gas companies out there just put a new oil drilling platform out in the Gulf of Mexico. The oil drilling platform has 40,000 sensors on it, 40,000. So I'm like really curious. I'm talking, what are you guys doing with that data, right? And they go, well, actually most of it's digital exhaust. Digital exhaust. It's just going into the air, right? Why? Well, we're a little bit, in my opinion, in a catch-22 because you can actually go, well, okay, 40,000 sensors once a second. I mean, how much is it going to cost for me to store all this data? And I'm either going to make a hardware guy very happy or a software guy very happy because it's going to be a very large number, right? And then they go, well, let's assume that I even can say, well, it's going to cost me $50 million. Well, I got to walk into my boss and explain why is it or what we're going to get out of it. And here's where the issues of analytics and learning and collection intersect, because the common methodologies that are being used today are largely, BI, visualization, let me go hire 3 data scientists and go figure this stuff out. And so I think the opportunity to bring the world of AI, machine learning, which has been used, to great effectivity in things like speech recognition, can actually be brought into this world as well, and I'm heavily working in that space. And finally, if you look at it and say, well, so what, right? What does this matter to anybody? It's really cool technology, right? And here I counsel you to start to split the world into people that build machines and people that use machines. So the guys that build machines are like AGCO builds combine harvesters, GE builds MRI scanners, Goldwind builds wind turbines. People that use machines are, Children's Hospital of Orange County, farmers, utility companies. While they share the machine itself, their benefits are not identical, right? And let me just spend a couple minutes for you to think about this. In the world of people who build machines, right, gene sequencers, MRI scanners, wind turbines, combine harvesters, all these sorts of things, there is sitting in front of them an enormous opportunity and also a challenge, which is if you start to think about the machine of the future as a bunch of sensors, a bunch of actuators, a big computer in the middle with a lot of software on it, right? And I always point out to people, if you want to think about this, you can go see one in real world. It's called a Tesla, right? A bunch of sensors, a bunch of actuators, a computer in the middle. And by the way, you see a car where now, every couple months, you get new features in the car. I mean, this has never been done before, right? And so the advent of moving to machines which are driven hugely by software, right, enables us to see business models which are going to be completely different. So let me just touch on 3 for you to think about it. One is, some of you may be aware that GE's been very big into this thing, right? They run lots of ads. Well, why are they doing that, right? Well, in the world of software, what we did was we said, here, let me sell you this product. It's called ERP, purchasing, HR, whatever. And then let me sell you a service contract on that. At Oracle, right, prior to the Sun acquisition, we did $15 billion in revenue. 12 billion of that was for the service contract on it. If you go study GE's financials right now, they do 120 billion in revenue. 70 billion of that is selling you a jet engine, an MRI scanner, et cetera. 50 billion is selling you a service contract on that. Once you realize that service is, in essence, information delivery, you can start to appreciate that the margins on that business could be enormous. So the move for machine manufacturers, guys that make this stuff, to vastly transform their business models is heavily afoot. In the end, and I'll end there, we're going to start to see machines as a service, just as we've started to talk about software as a service. And just to give you a funny little example of this, there's a company in Brazil right now. I don't usually use consumer examples, but there's a company in Brazil right now where you actually don't pay for the tires anymore. You just drive in, they put new tires on it, and they charge you per mile. It's not a business from a model point of view you want to get into second. So with that, I ran all the way to the end, and I'll pass it back. Thank you.
Okay, and we're going to wrap up with an ethical framework.
Hi, good morning. First, I'd like to just poll the audience and ask anyone in here who's a clinician, please raise your hand and stretch it as high as you can. Okay, looks about like half. And who in the audience is a data engineer, data science, or someone technical? And I know several of you will overlap, so raise your hands high. And then who else is in the room, either from the business side or any category I haven't mentioned yet? Raise your hands high. Great. So it's really wonderful to see such a mix of people in this room. And today I'd really like to share a topic that I think is relevant to each one of us here. The topic I'm going to be talking about today is the issues of ethics, bias, and equity. And before I get into that, I'd first like to give you a little bit about my background. So my name is Wen Dombrowski. I'm a physician that specializes in the complex patients who have multiple diseases and often hard to diagnose. And a lot of my work has been focused on emerging technologies, how to develop it and get organizations to use it. And furthermore, my background includes 2 decades in ethics, bioethics, and philosophy. So combining this experience, I want to share some observations and some food for thought for today. Just to start off with a basic overview of medical ethics, the general framework traditionally has been these 4 principles of autonomy, beneficence, non-maleficence, and justice. And basically what this means is that in traditional medical ethics, the concept is how do we really make sure that patients get to choose what does or doesn't happen to them? And how do we make sure what's happening to the patients is good for them does not harm them, and is fair. Now, I want to talk about some, general benefits of artificial intelligence and related data technologies. So one of them is that the ability for algorithms to, provide relevant decisions, relevant guidance to both patients and clinicians. This can really empower them to make better decisions that are less harmful and promote more autonomy. And furthermore, this can improve the user experience both from the staff perspective as well as from the patient perspective, because there's easier access to information, easier access to care. The care can be either in person or virtual, whether that's through machines diagnosing cancers from an MRI image, or it could be machines that are providing telehealth and telepresence services. And also, one of the really exciting things about artificial intelligence is that it can actually provide digital accessibility. And what I mean by that is that there are oftentimes, traditionally I think when we think about computers, and people using computers, the traditional interaction has been through a keyboard or through a tablet. And with technologies like Alexa, this allows people who have various physical and cognitive deficits to be able to interact with computers and information sources. So with Alexa, for example, people who are not able to see or not able to type or not able to spell, they can still interact through voice and through other inputs. And then last, I wanted to mention functional accessibility, which is related to digital accessibility. So for people who have physical difficulties using technology or accessing physical care, these data, the technology tools that you can get from artificial intelligence allows more people to have more access to care. Now, on the flip side, one of the concerns that I have and that some of my colleagues have is that if you have algorithms that are automatically telling you what to do or automatically suggesting what to do, does that override the autonomy of the patient and the physician and other stakeholders in the healthcare ecosystem? And also, is it possible for these algorithms to actually recommend things that are actually harmful or unfair, either unintentionally harmful or unfair, or potentially intentionally harmful or unfair? Now, yesterday, Rachel, she talked about how she gave many examples of bias from the perspective of gender bias and racial and ethnic bias. And today I also wanted to mention that there are age biases. So for example, if you Google an image on, if you just go to Google and you do an image search on grandma, what you almost always see is a picture of a very stereotypical white lady with a specific type of blouse on. And it's not really giving you the whole variety of what grandmas from different contexts look like. And then on the language side, this relates partially to what Andrea was talking about. And when I talk about language, it's not just about is it English or French or German, but also, I'll give an example. So my dad, when he was trying to use Google Voice, he started talking at it, but Google Voice didn't understand his accent. Even though he's been a US citizen and an American for many, many decades, he has a slight foreign accent that Google just did not understand, and it was giving very funny or weird answers in response to his questions. And in addition to the demographic, in addition to biases that can be based on demographics, something that I think we haven't really talked much about in the community is, what about the cultural norms? What about our values? Because at the end of the day, if you have a machine giving you a recommendation of what's best is defined ultimately right now by humans and what humans value. And each of us might value something different. Some people value safety, some people value risk, some people, some people like pepperoni pizza, some people like vegetarian pizza. And if there is a system that is, generating if they're generating recommendations or predictions, that if it doesn't take into account all the possible inputs and the different personal preferences and the personality differences, then the outputs are likely going to be inadequate. So I also want to talk about, some more on the risks and benefits of artificial intelligence So in addition to helping diagnose disease and identifying treatments, I really am excited about the potential to identify social factors and environmental factors that contribute to health. And furthermore, we know that in healthcare, much of health is determined by behavior change, and that difficult problem of how do we get people to change their behavior has been so elusive within the healthcare community for so many decades. But I do think that artificial intelligence that helps us, identify people's personality, their preferences, their learning styles, and their emotional responses, these can all be used to create interventions that really lead to lasting behavior change that helps our health. And yet, on the flip side, I've been really thinking about if we are relying on systems that sense our emotions and categorizes our preferences, does this restrict our human experience? So, for example, on Facebook, when you see a post, you only get a few options about, you get thumbs up, heart, wow, angry, sad. But what if I feel a mixture of those feelings? Or what if it's melancholy or ecstasy or surprise or something that's not in one of the official categories that's currently being collected and coded for? Are systems going to misinterpret the way you and I feel, and is it going to generate a response or recommendation that doesn't really reflect what we need? And also, as we rely more and more on artificial intelligence systems to help us understand other people's emotions and understand language and interactions, are we going to lose our own abilities to interact socially, to have common sense, and to trust our own intuition rather than solely relying on a machine? And in addition to this, there's part of the space that I'm in, I've done a lot with elder care, and there's been a lot of talk about how do we create virtual avatars to help the lonely older adults who are at home alone. And I do think there's a lot of potential benefit for virtual agents to help this use case. But on the flip side, what we don't know yet is there potential harm in terms of we're intending to create these virtual agents that are supposed to be helping people feel less lonely, helping people feel more valued, but as they interact more and more with machines and less with humans, does it actually create an opposite effect? I also want to mention that a lot of talks in this conference have centered on the specifics about data mining, EMR data, claims data, and research articles. And I really, really want to emphasize today, if there's nothing that gets remembered from my talk, if you could just really keep this point in mind. So EMR data is not complete data. It only represents a very small subset of truth. And even that small subset is in and of itself not objective per se, because if you have a blood glucose number in an EMR profile, for example, it's not really obvious just from that number itself, when was it taken? Was it before I ate, after I ate? Was it with, what type of machine was it taken on? What units of measurement was it done on? And then some of the other limitations are that the symptoms that are collected in the EMR, as well as the social history, is now constrained by these what I would call really dumb UI templates in EMRs, and it's not capturing a natural narrative of what the patient is experiencing, but really constraining it to preset categories of what is meaningful for billing usually. On the claim side, a lot of people are analyzing pharmacy benefits data, but that only includes what's prescribed and not necessarily what people are taking over the counter. And on the ICD-9s and ICD-10 side, these are diagnosis codes that basically physicians and billers only are coding for what they can get paid for. So there are a lot of people, especially with rare disease or maybe less paid for diseases, that are not being reflected in these data sets. And the last thing I wanted to mention is publication bias. So not every topic in life is being researched. And of the things that are being researched, oftentimes the research results that have negative or neutral results are never published, or they're actually suppressed. So for example, depression medications, if there's a suicidal outcome, that's suppressed from the data. And then in these research studies, there's selection bias. It tends to be young, healthy men, because women of childbearing age and people with any other comorbidities are frequently excluded. And I think with that, I'm gonna stop, and I'm happy to take questions afterwards.
That's great. Can we get 10 minutes on the clock? So we'll have a little dialogue now, and if there are any questions, you can put them up. But let's have a little bit of takeaways. I actually fed a question in there about digital exhaust. I love that term. It's a terrific term. We see digital exhaust in healthcare, right? All these devices are churning data that doesn't get captured anywhere, just goes into the ether. Walt will tell you that, hey, I could use that data. I could do something with that data. We can mine that data to find something. I think we're entering a cultural shift from a model expert-based system where we start to imagine what we need to a point where we start to collect all of this digital exhaust. So let's start. What are your thoughts? I want you to expand on your thoughts on the future of digital exhaust.
The future, I like that. Future of digital exhaust. Actually, let me just turn it into a leadership conversation.
Yeah.
You know, one of the things I ask people, I go, well, when is CIO a path to CEO? And a lot of people look at me like, oh, that's crazy talk, right? And then I go, well, okay, so who's the CIO at Amazon? Who's the CIO at Google? Who's the CIO at Facebook? And, you know, yeah, I know there's some guy managing the back office SAP system or whatever the hell it is. But at the end of the day, the CIO at Amazon's Jeff and, you know, Zuckerberg. I mean, software and their business is totally intertwined. These are not separate ideas. And I think, you know, if I look across the industries, right, power, water, agriculture, healthcare, et cetera, the gap is enormous right now. In fact, I went and did a talk to all of Jeff Immelt's direct reports at GE about 2 years ago, and I decided the title of my talk would be, Why is Hardware Not Software? Because, you know, these are guys that are mechanical engineers that got trained to go, you know, build jet engines. And software is the furthest thing from their mind. And I think the challenge of digital exhaust is really actually a leadership challenge. And I think until, you know, we get a turn of leaders or until we get a rise of new types of leadership, people are going to treat IT and data and all this stuff as, yeah, you know, when's my email server going to be back up? Which is all anybody thinks the IT department at any of these institutes are. They're just there to keep email running. And I think we need that shift, I mean, frankly, across the board.
Walt, you're developing one of the most cutting-edge technologies in cognitive computing. What are your thoughts on digital exhaust? Are we going to get to the stage where instead of prescribing what data we need, we can just ingest almost anything, any data type? How feasible is that?
Yeah, so the way we're looking at this is, you know, that there's an enterprise optimization for handling this data. You know, Anthony mentioned we really need to transition our perspective on databases. So going beyond relational databases and you know, being able to, we're working with a number of companies that are making that transition, setting up centers of excellence to handle these hypergraph approaches. So that's part of it. The other part is Saffron also has intellectual property assets at the device level. So being able to compress cognitive compute to the device to handle, you know, the tens of thousands of sensors, like, you know, one of our customers is, you know, one of the top companies that builds airplanes where there's 100,000 sensors on every airplane. So we are getting into this digital overload, if you will. But when you combine the salient data signals from those sensors where you can have a memory of it and remember the most important salient data signals, but also combine it with the other unstructured data sources, for example, mechanic notes, pilot notes, in the case of predictive maintenance. That's where we've had a lot of success at, you know, going from 5 data sources to 100 data sources just with one use case, where that then in turn informs supply chain. But you can imagine how that would also apply to healthcare as it relates to, you know, predicting and prescribing, you know, with these various data sources, but doing it in a way that starts to assimilate across the unstructured, structured data world, also bring in the device piece, especially next-gen medical devices. That's something that we're looking at as a fantastic opportunity. So.
Fantastic. And you know, going back to the leadership conversation, there's no doubt that a lot of companies that traditionally thought of themselves as as a pharmaceutical company, for example, at one point Eli Lilly said, we are an information company. Hospitals are information businesses. They deal with information. Sure, you provide care, et cetera, but at the end of it, if you don't have the knowledge at your fingertips, you're not providing the best care. Knowledge is the best medicine. When there was a question that disappeared now, but it asked, can AI help us solve some of the ethics issues? Certainly the reason we want cognitive computing in healthcare is because there are a lot of problems we just can't solve. So if Sharif sees a family with autism, there's no treatment. There's other things you could do. If you see a patient with cancer, there's no treatment. But we can also think about ethics as a really hard, complex problem. Can AI help?
I definitely think AI can help solve the ethics and equity issues. And, if the algorithms are trained in a biased way, then it will exacerbate the equity and bias issues. But at the same time, you can actually proactively, everyone in this room has a role in, helping proactively develop and test algorithms to really help level the playing field for everyone. And I think that, that could be anywhere from, I think, how would I say it? So there's this concept of humans tend to think that machines are more objective and that numbers are more objective. And I know we're in a room of people who understand this is more nuanced, but I think the general public has this belief that machines are always objective and that humans are always subjective. And while we know that's not always the case, we, as the professionals who are leading the AI community, we can really do what we can within our own organizations, our own projects, to try to mitigate the bias up front so that we're not dealing with the negative consequences afterwards.
Let me switch over to Andrea. There's a question right at the bottom. Don't let it disappear. How far does the ease of use of NLP? I mean, clearly, physicians are not ready to use some of the really sophisticated. You have a PhD in natural language processing. They don't. Will it be easy to use someday?
Well, I think we're definitely seeing a strong transition and push for these technologies to be adopted. And what I've seen work very well in practice is this integration of active learning into already deployed NLP solutions. Because the main concern physicians or health practitioners have is that the NLP system will make an error, and it will keep on making that error, and then it becomes tedious to always ignore it. With active learning, you can basically retrain the system on the fly, and it can adopt better knowledge and improve itself as you're using it. And I think this combination of a very powerful, complex mathematical solution integrated into an active learning framework is the future of bringing the NLP technologies in the clinical care.
So let me come back to Walt again. You guys have taken a little bit of a different approach to NLP. You want to talk a little bit about the difference, and maybe we could just take a step higher and talk about the difference between NEAT and Scruffy, the difference between expert systems that are built to do one very specific NLP type challenge versus a system that has a more general framework that allows it to interoperate between various cognitive challenges.
Yeah, so for those that are familiar with AI over the last few decades, obviously the semantic world was what it was focused on. And versus the statistics machine learning, handling more of the structured data. So what Saffron, the unique approach it took was taking associative memory that can handle at the individual entity level, whether it's unstructured data or structured data, being able to unify that into one knowledge representation was the first step. That was a fundamental key in developing this learning system. But the other piece was being able to be model-free, rule-free a priori. We can actually incorporate rules, we can inform modeling, learn from models, so it's not like that goes away. But as far as being able to look at unstructured data without a rules-based approach or a logic-based approach, as well as predicting what the predicate is, as far as the contextual elements that bind these different entities together, now we're taking this rule-free, model-free approach across that unstructured data where we can look at the network of associations across that clause, like whether it's progress notes or mechanic notes or whatever it is, and be able to understand the entity associations in that particular section, but also across the sections that we learn about. And taking that more broad, higher order approach to it is where we've seen a lot of success.
Well, we'll end on that high note. We've got just a terrific future to look forward to, and we had a great glimpse into that. Thank you to the panelists. We'll just give them a round of applause. Thank you.